Section 10.3, multiplying and simplifying radical expressions. Here's the main property of this section. Product rule for radicals. If you know that the nth root of A and the nth root of B exist, so if both of these exist, then their product is the same thing as the nth root of the product between A and B. Okay, so in words, the nth root operation and the multiplication commute. So if you take the nth root second, after taking the product is the same thing as taking the product first after taking the nth roots. Okay, I wanted to contrast this with, contrast this with a property that we learned in the previous section. Namely, I'm talking about this, the power of a product. Remember, at the time we called the power P, I think, at the time. And that P can be any rational number. So how about taking 1 over n? Obviously here n, it's implicit, but the n is supposed to be a natural number. So we know that the power of a product is equal to the product of the powers, right? We know that this holds at the time. Correct? And that's exactly the same. I mean, that's exactly the same thing. So this property is not a new property. It's just we're just highlighting it in some sense. We're specializing the power P to be 1 over n. Okay. All right. Let's do a few examples. Let's start with this. This is on page 720, number 14. And what we need to do is to multiply this this expression with this expression. Well, by the product rule for radicals, you're given the left side, you can transition to the right side while preserving the value. So you have an equality. So this becomes the sixth root of x minus 5 to power 1 times x minus 5 to power 4, right? So what are we using? What's the dictionary between this property and this current example? The 6 is the n, the x minus 5 is the a, and the x minus 5 to power 4 is the b. So we get this, and this is simply, this is simply the sixth root of x minus 5 to power 5, right? Because here supposedly this is a 1. So we're multiplying two exponential expressions with the same base. We keep the base, which is x minus 5, and we add the powers, and 1 plus 4 is 5. Okay. 20. Same thing. I'm still gonna apply the product rule for radicals, this one. The n is 9, it's the same n. The a is this guy, 12x squared y cubed, and the b is 3x cubed y 4. So this becomes the same as the 9th root of 12x squared y cubed times 3x cubed y 4. Correct? And the convention is whenever we don't write the operation, we mean it's a multiplication, right? So this is a multiplication here, a multiplication here, a multiplication here, and a multiplication here, correct? All right. And so now we can perform the product before we perform the 9th root. So this is the same then as the 9th root of 12 times 3 is 36. x squared times x cubed, it's the same base, so we keep the base and we add the powers. 2 times 3 is 2 plus 3 is 5. And similarly for the y cubed times y4, y cubed times y4 is y to power 3 plus 4, and 3 plus 4 is 7. Correct? Keep the base, remember, when you multiply two expressions, you keep the base, having the same base. You keep that base and you add the powers. Okay. All right, so let's do this definition. Let's read it. An integer n is said to be a perfect kth power. Here k is supposed to be a natural number. So we said that n is a kth power if you can find an integer m such that n is the kth power of m. Okay. So if you can write n as the kth power of an integer, then we say that the integer n is a perfect kth power. For instance, 49, take n to be 49, is a perfect second power or perfect square, right? Because, why this is the case? Because we can write 49 as 7 squared or negative 7 squared, right? So n is 49 and m is that guy that exists, and which is 7 in this case, and k is that thing. So if k is 2, which is this phrase becomes the second power, and as such the idea is, can I write 49 as the second power of some integer? Yes, we have 7 and we have minus 7. Just choose one of them. It's about the existence of such an integer, right? So 7 does the job. 8 is a perfect third power. So 8 is n and k is 3. So this is the case because, so the idea is I can write 8 as something cube, correct? Some integer cube. And that integer is 2, correct? So since you can write 8 as the third power of something, we say that 8 is a perfect third power or a perfect cube, correct? All right. Definition. We say that a radical expression of index k, remember what's the index of a radical expression? The index is the guy that sits on the hand, right? For example, the index here is 9, right? So it's 9. The index here was 6, and so on. The index here is n. So a radical expression of index k is said to be simplified. So we're defining the word simplified. Whenever it's radicand, what's the radicand? The radicand is the guy that sits under the umbrella. So in this case, 12x squared y cubed is a radicand of the first expression. 3x cubed y4, y to the power 4, is a radicand of the second one, right? And so on. So one more time. A radical expression of index k is said to be simplified provided its radicand has no divisors or factors other than one that are perfect kth power. Okay. Just allow a little bit of time for this definition to sink in. Let's read it one more time. A radical expression of index k, we say it's simplified whenever its radicand, the guy under the umbrella, has no divisors other than one, which are perfect kth power. Remember, perfect kth power is what we just talked about above, right? For instance, square root of 10 is simplified. Why? What are the integers that divide, that are the factors of 10? Let's just talk about the positive ones. Well, 10 is made up of 2 and 5, right? These are the building blocks. These are the primes that make up the 10. Correct? And none of these is a perfect second power. Remember, when we don't write the index, the assumption is that this index is 2, right? Remember that? So whenever we don't write the index, we mean that this index is 2. So the idea is here, the square root of 10 is simplified, according to this definition, because I cannot find a factor or a divisor of 10. What are the factors or divisors of 10? 2, obviously 1, but we're not talking about 1. 2 and 5. And 10. So these divisors, none of them is a perfect second power. Why second? Because the index is 2 in this case. So none of the divisors is a perfect square. As such, this guy is simplified. Square root of 42, similarly. Square root of 42. How do you write 42? What's the prime factorization of 42? Meaning, let's write 42 as product of primes. Well, 42 is 6 times 7, and 6 is 2 times 3, right? So this is the prime factorization of 42. And none of these factors is a perfect square. Remember, the index is also 2 here. So none of these factors is a perfect second power. As such, this is also simplified. Correct? Square root of 54 is not simplified. Why that's the case? Well, 54 is 27 times 2, and 27 is 3 squared, so 3 cubed. So there is a factor here. There is a factor that's a perfect second power. We're still talking about the index being 2. Let me highlight this again. We're still talking about the index being 2. So what's that factor that's perfect second power? Well, it's the 9, right? Because remember, the divisors here are 2, 3, 6, 9, 18, and so on, right? So is there any of these factors? Can you come up with a factor that's a perfect second power? If yes, this is not simplified, and we just found it. 3 squared, which is 9. It's part of this. It's a factor. It divides this product. Since this factor divides the radicand and it's a perfect square, this is not simplified. So since 3 squared is a divisor or a factor of 54, right? We just violated this the definition. So I was able to find a divisor, namely 9, which other than 1, which is a perfect second power for that 54. So the square root of 54 is not simplified. The cube root of 12. Well, 12 is 2 squared times 3, right? 4 times 3, so 4 times 3. So the question is, can you find a divisor of 12, which means this product, which is a perfect third power, a perfect cube? Well, there's no factor here. There's no prime number that's needed 3 times in order to make up 12. Okay, let's say it this way. Over here, I needed 2 times in order to come up with this number 54. The prime 3 was needed twice. So that twice thing is 3 squared, which is 9. That's the factor of 54. Over here, I don't need a prime number. I don't need more than I don't need 3 copies of any prime numbers to write 12. Okay. As such, this is simplified. The cube root of 16 is not simplified. Why? What's the prime factorization of 16? Well, it's 2 to the power 4. So is there a factor that divides 2 to the power 4, which is a perfect third power? Yes, 2 cube, right? 2 cube is part of this writing. So 2 cube divides 2 to the power 4. It's because 3 is smaller than 4. As such, there is a perfect third power that divides the radicand, and hence this is not going to be simplified. So because 2 cubed, which is 8, is a factor of 16. Okay. All right. 721, page 721, number 24. Simplify by factoring, obviously, but simplify. Well, 28 is 4 times 7, right? Correct? 4 times 7, and 4 is 2 squared. So what did I do here? I wrote the prime factorization of 28. This is it. What's the index here? The index is 2, right? Okay. So I need to simplify it, which means I need to write, which means they're telling me in some sense that this guy, 2 squared times 7, which is 28, has a perfect second power. It's apparent at this point. The 4 is a perfect second power, which divides this radicand 28, correct? So this is the same as by the property that I need to simplify it now. I need to simplify it because I found that 2 squared is a factor of 28, which is a perfect second power. So now I'm going to use the property, the product rule for radicals, this one. I'm gonna use it from right to left this time. I have the 2 squared as a and the b as 7, and the n is 2. So I'm gonna use it from right to left. I'm gonna write the second power of 2 squared times the second power of 7. And I'm gonna get the second power of 2 squared times the second power of 7. Correct? And what's the second power of 2 squared? This is simply 2. So the answer is 2 square root of 7. Correct? And look at this. Obviously, this radical expression is simplified because 7 doesn't have a divisor other than 1 that's a perfect second power. And I'm allowing 1 to be the only divisor, right? As such, this expression is simplified according to the definition just mentioned. Okay. Cube root of 54. Well, we just dealt with 54. The prime factorization of 54 is 3 cubed. 3 cubed times 2. Correct? 27 times 2. And now it's apparent that one of the divisors, or there exists a divisor of 54, which is this whole thing, which is a perfect third power, right? It's right there. 9 or 27, sorry, my bad. 27 is a perfect third power. So since 54 has a perfect third power divisor, this is not simplified. And the idea to simplify it is to, again, use the product rule. Is to use the product rule for radicals and use it from right to left this time. The a is going to be 3 cubed and the b is going to be the 2. Okay, so let's do it. So I'm going to use the product rule here, and then I'm going to get this times this, right? I wish you highlight these equalities because I'm just commenting. I'm not highlighting them here, but in your own notes, I wish that you actually highlight what each equality is, uh, or why each equality is holding. So for example, here you may say, oh, this is holding because, so I'm using the product rule for radicals with the a in the product rule. The a over there is 3 cubed, and the b over there to be 2, right? So it would be useful to actually write these in your notes everywhere. I mean, just to highlight why each equality is true. Anyway, so back to this. And what is this? The third power of 3 cubed. Back to an earlier section here. The third power of 3 cubed, this is 27. So I'm looking for a guy so that if I cube it, I'm gonna get 27, and that guy is clearly 3. Remember, the x cubed function is 1 to 1, so once you find a guy, that's the only guy. So 3 is the guy, or a guy, then it's the only guy. So long story short, that guy is 3. And we get the answer to be 3 times the cube root of 2. Right? Certainly this radicand 2 has no divisor other than 1, which is a perfect third power. So this is simplified. And hence I answer the question. Okay. Recall this. For any real number, remember here I used it, the index here is 2, right? So this looks like the nth root of an, and this looks the same thing as the nth root of an. So recall this thing. For any real number a and natural number n, the nth root of an, so something like these, is equal to the absolute value of a if n is even, and it equals a if n is odd. I'm aware that we only proved it when n is 2, but the same application or the same proof is going to hold for any n that's even. Okay, so we showed at the time the square root of a squared is absolute value of a. In this case, n is 2, which is even. But the same thing, just revisit the definition of the nth root when n is even and compare it to the second root or the square root. They're very much the same, but the n is different. I mean, that power is the only thing. But the requirement to find this guy is the same, and hence I'm expecting the same result. When n is odd, there's no confusion. There's one and only one guy that does the job, because the function x to power odd is always 1 to 1. So once you find a guy that does it, that's the only one. Okay. Over here, remember the bars, the absolute value is because we found there are two guys. If a does the job, negative a is also going to do it, correct? Because you are raising it to an even power. And even power absorbs signs, right? Anyway, so let's recall this. We're going to put it in action immediately. So the nth root and the nth power, they kind of undo each other in a clean way when n is odd, but in a quasi-clean, let's say, meaning I'm picking up absolute value for that guy a if n is even. Okay, let's do 31. The cube root of negative 16 times x squared times y cubed. Okay, so what I'm going to do is I'm going to use the product rule for radicals, the one that we just defined above, and I'm going to split it immediately. So what are the factors here? I have this guy times x squared times y cubed, correct? Sure, the product rule handles just two up 2 factors inside the umbrella, but you can, I mean, if you have 3, which is the case here, it's not hard to show that the same thing is going to apply, because you can think about these two as one package, split it for these two, right? So use the product rule, let's say, for this package as A and this package as B. Okay, and what do you get? You get the third root of negative 16 times x squared times the third root of y cubed. Correct? And let's do it one more time. Let's apply the product rule again, but now A is negative 16 and B is x squared, and let's split them. So you get this. Correct? So a couple applications of the product rule for radicals allow me to transition from the third power of negative 16 times x squared times y cubed to the product of each of these individual radical expressions. Okay, so I want you to keep in mind that even though this property is stated just for a radicand that looks like A times B, but you can actually inject, finitely many factors, as many as you wish, by keeping the same spirit of that property. The application is you apply it 2 at a times. Okay, long story short, the nth power of a product, regardless of the amount, as long as the amount is finitely many factors here, is the same as the product of the nth roots. Okay, so from now on I'm gonna skip this first step. I'm gonna just transition from this to that. All right, next. Negative 16 is negative 2 to power one more time. So negative 16 is, I would like to simplify each one of them, right? Let's find the prime factorization of negative 16 if we isolate the negative 1 by itself. So I get this, right? And 16 is 2 to power 4, right? Let's write it immediately. And I get this. I cannot simplify. This is already simplified because I needed only 2 copies of this guy x to come up with this radicand x squared. So I have no factors other than 1 for x squared. That's a perfect third power, correct? I don't have, in other words, I don't have an exponent here that's 3 or more. Okay. And this last one, this looks like the nth root of an, and we just talked about this. The nth root of an is a when n is odd, and the n happens to be 3 in this case. So that guy is simply y by this, right? Because n is 3 and n is odd, so that the nth root and the nth power undo each other in a clean way. So we get this. So this is y. Okay. All right, so I still need to simplify this entity. Okay. Let me cram it right there. So this is the same as the third root of negative 1. I'm using the product rule again, times the third root of 2 to power 4 times the third root of x squared times y. Correct? This I'm just copying. I used, for the first 2 expressions, I just split this. I split this thing by using the product rule. -1 as a, 2 to power 4 as b. So I get this guy, right? Okay. All right. And what's the third root of negative 1? What's the guy you multiply by its set 3 times, you get, what's the real number? that once you multiply it by itself this amount of time, 3 times, you get -1. That's -1. How about this? How about this? Well, how should I do this? This is the same as the third root of 2 cubed times 2, right? So let me write it better. So 2 cubed times 2, like this, correct? Times what we had over there, so third root of x squared times y. Okay, and let's focus here. This is the third root of 2 cubed times 2. I can use the product rule again and see this as, and split this cube root of 2 cubed times the cube root of 2, right? So I can rewrite this as -1 times the cube root of 2 cubed times the cube root of 2 times the cube root of x squared times y. Okay. And what's the third root of 2 cubed? What's the nth root of an if n is odd? That's simply the a, which is 2. So this is simply 2 then. Okay. And what do we get? We get that this is -1 times 2 times the third root of 2x squared. I'm combining these two again because by the product rule, I'm using the product rule now from left to right. I have the third root of 2 times the third root of x squared, right? So this becomes the cube root of 2 times x squared. So it becomes the cube root of 2 times x squared, exactly as we wrote it here. So these two, you can bundle them up this way, times y, right? And this is the same as -1 times 2 is -2 times the y that exists at the end times that third root of 2x squared. This is simplified because we simplified that one as much as we can, and this is simplified because there's no factor of 2 other than 1 that's a perfect third power. Likewise here, there's no factor of x squared that's a perfect third power other than 1. Each one is simplified. There are of different natures, right? This is a pure constant, this is a variable, so then the product is going to become a simplified expression, a radical expression. So we're done. Correct? Okay. Let me just draw a line here. Okay. All right, let's continue. Let's do 44. Square root of 40 times x cubed. All right. The first step, I'm going to proceed exactly the same in all of the problems. I'm going to split them up first because 40, the language here is times, right? So I'm going to split them up by the product rule for radicals. So I'm going to get square root of 40 times square root of x cubed. Correct? And let's write the prime factorization of 40. Well, the prime factorization of 40 is 2 cubed times 5, right? And this guy is the square root of x cubed. And I can think about x cubed as x squared times x. Correct? Similarly, 2 cubed, I can think about it as 2 squared times 2. Am I correct? And here I'm going to split the 2. I'm going to get square root of x squared times square root of x. Okay. So what I'm going to get is, let's use the product rule again. Let's use it this time. Let's combine these two together, because 2 times 5 has no divisor other than 1, which is a perfect second power. I can combine the 2, and I get square root of 2 squared times square root of 10 times square root of x squared times square root of x. Okay, let's simplify each one. How much is this? Well, by this one, the nth root of n is 2 in this case, so it's even. It's the absolute value of this guy. Who's the guy? It's 2, the base 2. So the absolute value of 2 is 2 itself. So this is simply a 2 then. How about this? Well, this is very much the same, but this time is x who's a, right? This is the second root. The index here is 2. Second root of x2, x squared. So it looks like this. N is 2, which is even. I'm going to get the absolute value of x. I'm going to get the absolute value of x. Correct? Okay. And the answer is, that's going to be equal to, this is 2, and this is absolute value of x, and I have product, and product is commutative, so I'm going to take 2 times absolute value of x times the square root of 10, which is a simplified radical expression, times square root of x. And square root of x is simplified, square root of 10 is simplified, and they are the radicands. 10 and x are of different nature, right? One is numeric, which is just pure constant, 10, and the other has the variable x. So if you multiply the two, you're going to get a simplified expression, radical expression. So you get the square root of 10x, and again, this is simplified because the source of this, each one is simplified, and they are different nature. 10 is numerical, and x is variable, right? So if you multiply them, you can still have a simplified expression. All right, so this is the answer. But in 44, so this is on page 721, what they said is, assume that all the variables represent positive real numbers. So they're telling you that this is, yeah, choose an appropriate color here. They're telling you that the x is positive. So what can you learn about this then? This is simply x, right? This is simply x. The absolute value of a positive number is itself. Correct? So the absolute value of x is x because x is positive. And hence, you can rewrite the whole thing as 2x square root of 10x. Make sense? Okay. All right, this one. 46. The third root of y to power 11. Well, this is the same as the third root of, what I'm going to do is I'm going to go to the largest multiple of 3 in the exponent. Okay? What's the largest multiple of 3 in 11? Well, the largest multiple of 3 in 11 is 9. So I can rewrite this as y to power 9 plus 2, because 9 plus 2 is still 11, correct? So let me use this as a first step. So I get this. And this is the same as the third root of y to power 9 times y squared, correct? If you don't believe me, go backwards. Y to power 9 times y squared is, I have two exponential expressions with the same base. We keep the base, we add the powers. So these are the same. Okay? And this is the same thing then as the third root of y to power 9 times the third root of y to power 2, correct? This is simplified. This is a simplified expression. Why? Because there's no divisor for y squared, which is a perfect third power, right? We only need 2 copies of y to come up with this entity, y squared. So there's, other than 1, there's no factor of y2 that's a perfect third power. But this is not the case for y to power 9, because y to power 9 can be thought of as something to power 3. What's this power? What's this power? So y to power what cube is y to power 9, right? Well, whatever this power is, if I should multiply it by 3 and the product should be 9. So that power is 3, correct? Agree with me? Okay, times the third power of y squared. All right. Let me use a different color just to highlight what I'm going to be doing here. So we had y cubed, right? Okay, so look at this expression. And contrast it with this. Correct? Let me zoom out one more time. So contrast this with this. This looks like the third root of something, the red part, cube. So the structure is the same, where n is odd. So what do we get? We get that that this guy is simply the a, and the a is the red part, which is y cubed. Correct? Okay. So this is y cubed times third root of y squared. So one more time, the last step, this looks like the third root of a cube, right? Third root of a cube. So this is of the form nth root of an. That's the a. And the n is odd by this one. They undo each other in a clean fashion. So you get only this part, which is y cubed in this case. Correct? And this is simplified, and that's it. We answer the question. The question is simplify. 48. Well, 48 is the third root of x cubed times y to power 17 times z squared. Okay, so what I'm gonna do is I'm gonna split them up because I still have a product here in between. I'm gonna split them up using the product rule for radicals to keep homogeneity for each radicand, right? Like here, here I just have numbers, here I have x, so I'm gonna just keep homogeneity within each radicand. So I deal with each variable by itself, and then I combine the simplified version of each at the end of the day. All right, so let's split them up. You get this. correct? And then what is that? We just dealt with this. Third root of a cube. Third root of a cube, when n is odd, it's 3 in this case, we get a. So we're going to only get x here, this x. Times third root of y17. Certainly I needed more than 3 copies of y to cover y17, right? I'm going to use the largest multiple of 3 needed to come up with 17. What's the largest multiple of the index? The largest multiple of the index is in 17. Well, the largest multiple of index in 17 is 15, because the index is 3. So this can be written as the cube root of y to power 15 plus 2. Am I correct? Times the last part, which is already simplified because we didn't need more than or 3 more than let me say it one more time. We did not need at least the index amount of z. We didn't need at least the index amount copies of z to come up with the squared, correct? We only needed 2 copies of z to make up the z squared. As such, z squared is then going to have a divisor other than 1, which is a perfect third power. And hence that expression, the whole thing is simplified. So I cannot do much better than this. I'm going to just keep it. Still have work to do in on the second expression. How are we going to do it? Well, we're going to handle it in a very similar way as we handled at the time. What is it? Y11. Correct? What did we do? So we split them up. So we're going to write y15 times y squared. Split them up. And then split that product. And then this one is going to be simplified via this. Via this property. Correct? Let's do it. So we're going to get x times the third root of y to power 15 times y squared times the third root of z squared. Okay, that's going to be x times the third root of y15, as promised. I'm using the product rule now, times the third root of y squared times the third root of z squared. This version is, or this expression is simplified, right? This is simplified. Why? For the same reason this is simplified. We needed less than the index amount of copies of that base y to come up with, or to make up the y squared. So I don't have a factor other than 1 that's a perfect third power, a factor of y squared that's a perfect third power. So as such, this is simplified. So this is simplified, this is simplified. The nature of these expressions are different. This has variable y, this has variable z. So if you multiply them out, you're going to have a simplified expression. So this is good. This is good to go here. I still have to simplify the third root of y15. Well, y15 is the same as what? Y15 is the same as something cube, right? This is a perfect third power. This guy is a perfect third power. Well, the base is y to power 5, right? If you multiply y to power 5 3 times, you're going to get y to power 15. Okay. Times, let's multiply these out. We just talked about it. This is already simplified. So let's combine them. And what is this? This is the nth root of an. Who's the a in this context? Is y to power 5. So it's the nth root of an, and n is odd because it's 3 in this case. So we're gonna only get a. So we're gonna only get a, which is y to power 5 in this case. Correct? So we simplified this radical expression, and that's the simplified version. And why it's simplified? Because this radicand this time, y squared z squared, has no divisor other than 1, which is a perfect third power. Okay. All right, 56. The fifth root of 64 times x to the power 7 times y to the power 16. Well, same process. I'm going to split them up as a first step. I'm going to write, let me change the color so we can distinguish the two. How about the green this time? The fifth root of 64 times the fifth root of x to the power 7 times the fifth root of y to the power 16. Same process. For 64, well, 64 is 2 to power how much? 64 is 8 squared, right? So it's 2 to power 6 then. Am I correct? Because 2 cubed is 8. Square that, you get the 6. So that's going to give you the 64. Okay. All right. So did we need more than 5, or did we need the index amount of copies of 2 or more to make up the 2 to power 6? In other words, is 6 bigger than or equal to 5? Yes. So as such, I'm going to be able to simplify this first radicand, because there is a divisor of 2 to power 6 that's a perfect fifth power, which is 2 to power 5, right? 2 to power 5 is a divisor of 2 to power 6. Okay. And this one too. 7 is bigger than 5. This means there exists a divisor of x to the power 7 other than 1, which is a perfect fifth power, namely x to the power 5. And this one as well, right? Okay. So in each one, the way I'm going to proceed is as we started here. For example, in the 17, how did we start? Just keep track of this, all this part. How did we do it? We started by writing 17 as the largest multiple of the index, which at the time was 15, plus the rest. So what you're doing is you're dividing 17 by 3, right? If you divide 17 by 3, then the quotient is 5, right? So 5 times 3, which is 15 plus 2. Okay. And then you split them up. Y to the power 15 plus 2 is y to the power 15 times y squared. And then you use the product rule to split this product, right? Remember the nth root and multiplication commute. So you do this. And then 15 is 5 times 3. So y to the power 15 is y to the power 5 times 3. Or y to the power 5 to the power 3. Because 5 times 3 is the 15. And then that becomes y to the power 5. Correct? And then the leftover, this part is simplified, because you needed less copies than this index to make up, less copies of y to make up y squared, less copies than the index of y to make up y squared. Okay, so this is this process that you see here, which is also the same as when we dealt with y11. It's gonna be applied over and over. Okay. So at the end of the day, what you're gonna be left with, and the power is only the quotient when you divide this number by this number. So you can abstract it actually and come up with a nice formula. I'm not going to complicate it for you. I'm going to just keep doing the same thing over and over. So technically what's going to come out is simply the quotient between 17 and 3. When you divide 17 with 3, you get 5 as a quotient, and the remainder is 2, right? All right. Anyway. Okay, so back to this. This is the 5th power of 2 to the power 5 times 2, correct? Because 2 to the power 6 is 2 to the power 5 times 2. Similarly for the next one, x7, the highest multiple of the index, which is 5. The highest multiple of 5 and 7 is just one time. So you get x to the power 5 times x to the power 2, correct? And then the last entity, the highest multiple of 5 and 16 is 15. So you're going to get y15 times y, correct? Because y means y to the power 1. y15 times y to the power 1 is y16. And why did we split this way? Because 15 is the largest multiple of 5. 15 is the largest multiple of 5 and 16. 5 is the largest multiple of 5 and 7. 5 is the largest multiple of 5 and 6. Okay, all right. And this is the same as the 5th power of 2 to the power 5 times the 5th power of 2 by the product rule for radicals. 5th power of x to the power 5, 5th power of x squared times the 5th power of y to the power 15 and times the 5th power of y to the power 1. Correct? Okay. This is simplified. This is simplified, and this is simplified. And all the rest are non-simplified, and I still need to deal with them. Correct? Okay. Here. What's the nth power of an? That's a, because n is odd. Talking about this. Oops. Talking about this. When n is odd, this guy and this guy are the same. Okay. So this is simply 2. I'm copying the second part. And then, for the same reason, the nth root of an when n is odd is simply a. So this is simply x times the 5th root of x squared times the 5th root of y to the power 15. And y to the power 15 is the same as y to the power something to the power 5, right? And that thing is clearly y cubed. Correct? I mean, 15 is a multiple of 5, so certainly that guy y to the power 15 is going to have a divisor, which is a perfect 5th power. Yes? Okay. And times, at the end of the day, this 5th root of y. Okay. Okay, so how about this one? What is that? Well, it's very much the same as this guy, same thing. The 5th root of something to the power 5, because the index n and this power is the same, and both of them are odd, that thing is odd, then they clean up in a nice way, and you get y cubed, right? So the 5th root of a to the power 5, is simply a. So we get that. Okay. And now I'm gonna highlight the ones I'm gonna combine. You see this one here, and this one? I'm gonna multiply them out because each one of them is simplified, and they are of different natures. This is numerical. This is the radicand is a variable expression in terms of x, and this is a variable expression in terms of y. So if you multiply them out, you get a simplified radical expression. Okay, and I'm gonna multiply out the rest. So outside I'm gonna have 2 times x times y cubed. So 2 times x times y cubed times all these oranges. So the fifth root of 2 times the fifth root of x squared times the fifth root of y. By the product rule, for radicals, I can just condense the 3 and write the fifth root of 2 times x squared times y. I realize that this factor here is has no divisor other than 1. That's a perfect fifth power, right? Because none of the previous one did. All right, so we get that. 60. The fourth root of x minus 2 to power 14. Well, that's the fourth root of x minus 2. What's the largest multiple of 4 in 14? What's the largest multiple of 4 of the index in 14? I'm still proceeding exactly the same way as we did before. But the largest multiple of 4 in 14 is 12. So I can get 12 plus 2 here, right? I'm going to apply again the same process. Obviously, whenever you start being more comfortable, you can start shortcutting and you can have your own perspective, right? But since I'm presenting it to an audience, I'm gonna just have a uniform approach, and it's your job to actually figure out how to shortcut things. And the more you do, the more familiar you become with it, and obviously, the faster you become. Okay, so we get the fourth power, or the fourth root, I should say, of x minus 2 to power 12 times, all right, let's do it. Let's do it in steps again. So this is the same as x minus 2 to power 12 times x minus 2 to power 2, right? Because this product remains x minus 2 to power 12 plus 2. Okay, and now I'm going to use the product rule for radicals. I'm going to let the fourth root commute with multiplication. So I'm getting then this and this. Correct? This is simplified because the exponent for that base is smaller than the index. This is not simplified, and obviously I'm gonna have a perfect fourth power, a divisor of x minus 12 to the power 12, which is a perfect fourth power. And that thing is x minus 2 to the power 4, right? Okay. Let's keep doing what we've been doing. If you see the answer, great. If not, stay with me. So we get the fourth power of, so as we said, we're going to have a divisor of x minus 2 to the power 12, which is a perfect fourth power. Who's that divisor? Who's that base? That base is x minus 2 to the power 3, right? Correct? Because 3 times 4 is 12. All right, times that simplified expression. So we get this. Okay. And now, just to be clear, How about I erase this and write it in different colors so you can see it better. So we had x minus 2 to power 3, correct? So what's the setup here? The setup is the nth root of an, the nth root of an, the nth root of an. That's the absolute value of a if n is even, and n is even. In this case, it's 4. So the absolute value of x minus 2 cube is the answer, right, for this. And the absolute value of x minus 2 cube is the same as the third power of x minus 2, okay, times the fourth root of x minus 2 squared. All right. So that's the answer for this. 35. F of x is equal to the third root of 32 times the third power of x plus 2. Okay, so for 35, the question is simplify as well. Okay. All right, so this is the same process. I'm splitting them up and using the product rule for radicals, and then get this. Okay, and the third root of 32, what's the prime factorization of 32? Well, it's 2 to the power 5, am I correct? So that's the same then as, what's the largest power of, what's the largest multiple of 3 and 5? It's 3 itself. So we get the third power of 2 cubed times 2 squared, right? Because 2 cubed times 2 squared is 2 to the power 5, times this. This is the nth power of a n. It's the same n, and it's odd, so they undo each other in a clean way, and you get x plus 2. Correct? All right, and then I'm splitting this product using the product rule. Okay, and that's exactly a 2 for the same reason as we've been discussing. And the answer is 2 times the x plus 2. So it's this guy, just 2 times the x plus 2 times this piece, which is simplified again because the power is smaller than the index. Right, so it doesn't have other than 1. It doesn't have a 2 squared doesn't have a factor which is a perfect third power. And 2 squared is 4. Maybe it's better to write. Okay. All right. 38. F of x is the second power of 5 times x squared minus 10x plus 5. And 38, the question is also simplify. Okay. How about factoring out 5 from all these summands? 5x squared is divisible by 5, 10x as well, and 5. So let's factor out 5 and get x squared minus 2x plus 1. Correct? If you want to recheck your work, distribute the multiplication over addition and subtraction again, and get that this is 5x squared minus 10x plus 5. Okay. And what's x squared minus 2x plus 1? What is this guy? This is x minus 1 squared, am I correct? If you multiply x minus 1 by itself, you get, what's the square of the difference, a minus b? Well, a minus b squared is a squared minus 2 times ab, just 2x, minus 2x in this case, plus 1 b squared, which is 1, correct? And that's the same as the square root of 5 times x minus 1 squared. And this is the same as square root of 5 times square root of x minus 1 squared. Correct? And now this last radical expression, the index is 2 again. And what is that? This is the nth root of a n. The base is x minus 1. This is a. The nth root of a n. And n is even. That's going to be the absolute value of x minus 1. That's the absolute value of a. Correct? Okay. Very good. So that whole thing is absolute value of x minus 1 times square root of 5. So absolute value of x minus 1 times square root of 5. So writing the function as this or that, they're the same thing. Okay. Let me make a quick comment here. I'm not sure if this would be your thought here. But it is a common mistake. The square root of 5x squared minus 10x plus 5, some people may think, oh, I can write this as the square root of 5x squared minus the square root of 10x plus the square root of 5. So in other words, you're splitting up the square root, you're commuting the square root with addition and subtraction. So breaking it down to each one of these summands. In other words, you are using, let me zoom in here. In other words, you're asking if this is true. Correct? If you would like to split up the square root, to commute the square root with addition and subtraction, technically you are asking if this is true. And don't confuse this with the formula of this section, which is, where is it? Which is this guy. Correct? The operation here is multiplication. Over there it's addition. For multiplication, the property says it's true. But for addition, let's check. And let's check when the index n is 2 in this case. Well, how about we take nice numbers? How about we take a to be a 9 and b to be 16. What's the left-hand side? LHS for left-hand side. Left-hand side becomes square root of 9 plus 16, which is square root of 25, and square root of 25 is 5. Whereas the right-hand side is the square root of 9 plus the square root of 16. And square root of 9 is 3, and square root of 16 is 4, which is 3 plus 4 is 7. So left-hand side is 5, this guy is 5, and the right-hand side, this guy is 7 for this choice, for these choices of A and B. So the two sides do not match for these particular choices of A and B. As such, this is not a property, right? Remember, for for this to be a property, it has to hold for all choices of A and B where both of the sides exist. And when you find a counterexample, that thing uses its universality. It's not a property anymore. Correct? Because we have a counterexample. Sure, sometimes it holds, but it doesn't hold all the time. That's my point. If you take B to be 0, this is certainly a true thing if you take A to be a non-negative number, right? But the idea is it doesn't hold all the time, and this is a counterexample. So, no, the answer to this is no. For instance, choose A to be this and so on, right? So please, this is a wrong thing, okay? This is a wrong, how can I highlight this for you? How about writing a big X on top? Big X, just to remember that this is not a true thing. It was a question though, okay? All right, so please don't split them up in this fashion because, so don't split it up in this. In other words, what I'm saying is don't write this as this. Or something to this effect. Because if you do, you're kind of using that, right? Okay, so I want to erase this part again. Okay. Page 721, number 64. Multiply and simplify. So 64 is square root of 8x times square root of 10y. Well, let's multiply them out first by using the product rule for radicals. This is a multiplication. I can combine the two. This is not addition. The operation is multiplication here. So this is the same then as the square root of 8 times 10 times x times y, right? Okay. And 8 times 10 is 80. And I'm going to split them up like this, back. Why am I splitting them back? Just to simplify each one as much as we can. Correct? This is one is simplified, this one is simplified. We're good because the power here is 1, which is smaller than the index. Power here is 1, smaller than the index. Each one is simplified. I still have to simplify the first part. Do we have, certainly AD has a divisor which is a perfect square, perfect second power. So I can simplify this guy. Let's do so. How about finding the prime factorization of AD? What's the prime factorization of AD? Well, AD is 8 times 10, and 10 is 2 times 5. So this is going to be 2 cubed times 2, which is 2 to the power 4, times 5, right? So 16 times 5 is 80, times square root of x times square root of y. Okay. Let's split these up, because 5 by itself doesn't have a divisor which is other than one which is a perfect second power. So we get this. Times square root of x, square root of y. Correct? All right. What's the square root of 2 to the power 4? Well, I can think about 2 to the power 4 as 2 to the power squared squared. So that's the same as 2 to the power squared squared times, each of these is simplified and they are of different nature. So this is numerical, just pure constant. This is expression in x, this is expression in y. Each one is simplified. You can combine all three, get a simplified expression. So this is 5xy. Okay. And this is of the form nth root of an. Who's a in this context? A is 2 to power 2, right? Let me highlight it for you. Just color it in brown, correct? So this is of the form the nth root of a n, and n is even, the n is 2, right? So the what this is going to be is the absolute value of 2 squared, but 2 squared is positive, so the absolute value of 2 squared is 2 squared. So we get 2 squared times square root of 5xy, and 2 squared is 4, right? So we get this. Again, definitely you can find ways to do it faster and so on, so please develop your own way to kind of like shortcut or accelerate the way to get to the solution. Please express yourself in the solution. I'm giving you enough details so each step is kind of like clear, right? So each moving on from one stage to the next is not unclear. That's my point. All right, 66. The square root of 20x times the square root of 5x. Okay, about the blue this time. Okay. Well, how about using the product rule for radicals? So we get the square root of 20 times 5 times x squared. Okay. So this is the square root of 100 times x squared, which is the square root of 100 times the square root of x squared. Correct? Okay. And 100 is, square root of 100 is 10. And square root of x squared is absolute value of x, right? And in 66, they said all variables are positive. Am I correct? Let me just read it one more time. Yeah, all variables are supposed to be positive. So we can write that this is equal to 10x. And let me explain it here. Since we're given that x is positive. Okay, this is part of the question. If you're not given that x is positive, you stop here, right? You cannot do any better because you don't know what x is. It's if it's positive or non-negative, you get this. If it's negative, you get negative 10x. The answer would be negative 10x. Correct? Okay, 77. So 77. All right, so how about condensing them under one umbrella? So getting a big umbrella for the product. So we can do so because this is the product of the fourth root, the same index. So by the power rule for radicals, we can combine the two. So 8 times 2 is 16. Oops. 8 times 2 is 16. X squared times x to the power 4. Let's keep it. Y cubed times y. Y cubed times y. And z to the power 6 times z, right? Okay. Okay, so this is the same as the fourth root of 16 times the fourth root of x squared x4 times the fourth root of y cubed times y. Again, I'm preserving homogeneity of the radicand, correct? I'm preserving homogeneity of the radicand. The radicand here is pure constant. The radicand here is expression just in x. Here expression just y, and here expression in terms of z. Okay, let's simplify each one of them. Well, this is the same as the fourth root of 2 to power 4, right? And the nth root of an is absolute value of a if n is even, but the a is positive, so we get simply 2. Next one. This is the same as the fourth root of x to power 4 times the fourth root of x squared. This is simplified. The index here is smaller than 4. This is not simplified, and we can simplify it easily. The fourth root of x4 is the nth root of xn when n is even is the absolute value of x, and that remains the same because this is simplified. Okay, how about this one? Well, y cubed times y is y to power 4. And the fourth root of y to power 4, it's very similar to this, right? But the name of the variable is changed, so this is absolute value of y. And lastly, this one. This is the fourth root of z7. And what's the largest multiple of 4 in 7? It's 4 itself. So this is then the same as z to power 4 times z to power 3. Right? 4 plus 3 is 7. This is the remainder. 3 is the remainder if you divide 7 by 4, right? Okay. So that's going to be then the fourth root of z to power 4 times the fourth root of z cubed. Certainly this is simplified because there's no divisor for the z cubed other than 1, which is a perfect fourth power. In other words, the index here is small. The power here of this z, the base z, is smaller than the index, so this is simplified. And that guy is no different than this guy here and this guy here, but the name of the variable is changed, so this is absolute value of z. So absolute value of z times the fourth root of z cubed, right? Okay. So now putting things together, we get, what's the answer then? 2 times the absolute value of x. Let's put things together. So 2 times absolute value of x times the fourth root of x squared times absolute value of y and times absolute value of z times the fourth root of z cubed. And in 77 they said all the variables are positive. So the x is positive, the y is positive, and the z is positive. So the absolute value of each one is itself, right? So the absolute value of each one is itself. So this becomes 2xyz times the fourth root of x squared make it longer, x squared times z cubed. Okay, and the reason is we're given that the variables are positive. We don't need them to be entirely positive. Non-negative would be as good as any, right? because the absolute value of a non-negative number is itself. Anyway, so they gave it to us as positive, so be it. All right, so we get this. And why did we combine the last two? Because this is simplified and this is simplified, and x squared is an expression in x, z cubed is an expression in z. If you combine the two, if you multiply them out, guaranteed to be simplified, right? There's no factor of this guy, this radicand x squared z cubed, which is a perfect fourth power. Okay. All right. And let's do the last one, which is 80. Okay. Choose brown again. Okay, so let's try to do this a little faster. So the fifth root of, I'm using the product rule for radicals. So 8 times 8, so 64. X to power 4 times x to power 1, so x to power 5, right? Let's just put 5. The y cubed times y9 is y to power 12, am I correct? So y cubed times y9, you add the powers. And z cubed times z8 is z11, correct? Okay. All right. 60. Okay, let's split them up. So the fifth root of 64 times the fifth root of x5 times the fifth root of y12 times the fifth root of z11. Okay. 64 is 2 to power 6. Correct? We dealt with this before. Where is it? I forgot. We dealt with it before. It's right there. 64 is 2 to power 6. I think we dealt with the whole thing. And we found that it's 2 fifth root of 2 at the end of the day. So I'm going to just inherit that. So this was found before. This is 2 fifth root of 2. Correct? The second term, this is the nth root of a n, where n is odd. They cancel each other in a clean way, so you get x. How about this? Well, this is what? What's the largest multiple of 12 and multiple of 5 and 12? It's 10. So you can rewrite, oops, sorry about that. We can rewrite the fifth root of y12 as the fifth root of y to power 10 times y squared, which is the same as the fifth root of y to power 10 times the fifth root of y to power 2. And the fifth root of y to power 10 is the same as the fifth root of y to power 2 to power 5, right? Y to power 10 is a perfect fifth power, so it's y squared to power 5 times the fifth root of y squared. And now this is of the form the nth root of a, y squared is the a, n. So the nth root of a n is simply a when n is odd, because 5 is odd, so that thing reduces to y squared times the fifth root of y squared. Am I correct? Okay. And again, this is simplified because y squared doesn't have a divisor other than 1, which is a perfect fifth power. In other words, the square here is smaller than 5. And the very last thing is this guy right there. Oops, I chose the same color. I chose something else. This guy here, what do you think the answer is? Well, run the same program here, but instead of 12, put 11. Okay, obviously y has to be changed to z. 12, replace it by 11. This becomes 10, and this becomes 1. The 10 continues the same way, and the 1, instead of 2, is going to come here, right? So at the end of the day, it's going to be y squared, or z squared in this case, times the fifth root of z. So z squared times the fifth root of z. Correct? All right. And finally, for this equality, let me write it here. This is equal to 2 fifth root of 2 times the green x times the red expression, which is y squared times the fifth root of y squared, and this last one, which is z squared, the fifth root of z. Okay, and this is equal to 2xy squared z squared. So 2xy squared z squared. And then this simplified radical expression times this one becomes the fifth root of 2y squared z. Okay, and this is simplified because none of these entities, 2, y squared, and the z have a factor which is a perfect fifth power, other than 1, obviously. Okay. So finally, since we've been doing the same thing over and over to simplify a radical expression, how about we abstract the process? Just has one abstraction that encompasses all the previous discussions in some sense. If you don't like the abstraction part, don't worry about it. You can still do the same thing over and over, but for those of you who care about it, here's the abstraction. So in abstract, if we take n and m, two natural numbers, so they are positive integers, right? And a is a real number such that the nth root of am exists, then we have the following. The nth root of am, how do we simplify the nth root of am? Well, we've always been asking to start the simplification. The question was always, what's the largest multiple of n that exists in m, right? So in other words, we were dividing m by n. So we were dividing m by n. So we were doing long division or Euclidean division. So we were writing m as such a multiple of n, which means that we were able, we were trying to find the quotient so that if I'm multiplying by this divisor n, I get the dividend m plus a rest, obviously, right? A remainder. Let's call it r. And r is, the remainder is obviously at least 0 and smaller than n, right? Correct? So this is the long division. Okay. So for example, okay, I'll give an example at the end. And then we can rewrite the m as the writing you see in pink. So we get a to power n times q plus r, right? Okay. And this is the same as, if you remember, we used to split this. So we write a to power nq times a to power r, right? Because that's the same base. You can just add the powers, correct? Okay. And this is equal to, by the product rule for radicals, this is the nth root of a to power nq times the nth root of a to power r, right? This is simplified here because r is smaller than n, so there exists no divisor other than 1 of for an that's a perfect nth power, right? Because r again is smaller than n, so this is simplified here. Okay, maybe it's worth highlighting this. This is simplified. So it's simplified because r is smaller than n, right? Okay. All right, let's keep going. And what did we used to do here? So we write this as a to power q, the whole thing to power n. So we set the stage for the n. We set this, or we make it closer to for this expression to look like the nth root of something to power n, right? So we're gonna write this as the nth root of a to power q, the whole thing to power n, times this simplified radical expression a to power r, right? This is r here. Okay. And then because of this formula that we have, this one, the nth root of something to power n is the absolute value of the thing if n is even, and it's the thing if n is odd, right? So the thing here is a to power q. The thing here is a to power q. So we get that this is equal to two things. It's the absolute value of a to power q times the nth root of a to power r if n is even. And in the other case, when n is odd, they undo each other in a clean way. So we get a to power q times the nth root of a to power r, right? So this is if n is odd. Correct? So this is what we've been doing. This is the abstraction of the process. You can revisit earlier examples and replace n and n every time by the appropriate one. How about we do just one? How about the 5 and the 12? So if n is 5 and m is 12, if n is 5 and m is 12, this becomes 12 equals 5 times 2 plus 2, right? The remainder is 2 and the quotient is 2. So Q is 2, and here 5 is odd, right? So we get this format where Q is 2, so we get a to the power 2 times the fifth root of a to power 2, right? This is what we got here, right? That's exactly what we got here, and so on and so forth. For Z11, and we're talking about the fifth root, so M is 11 and N is 5. So this is gonna be, Q is gonna be 2 and R is gonna be 1, right? Because 11 is 5 times 2 plus 1. So this is gonna be written then as a to power 2, because Q is 2, times the nth root of a to power 1, and z to power 1 in this case, right? So we get this, and so on and so forth. We can use many earlier examples, and maybe one more with n even. How about this, which is the fourth root of z7. So n is 4, z is 7. So m is 4, n is 4, and z is what did I say? N is 4 and m is 7. Well, 7 is equal to 4 times 1, so Q is 1, plus the remainder 3. And we get this. So it's going to be the absolute value of a to power 1, so the absolute value of a times the fourth root of a to power 3. Right? So this is exactly what we found here. The absolute value of a times the fourth power of a to power 3. Correct? So so this is the abstraction of the whole process, and you can employ it anytime you want, or you can redo it every time you need it. Okay. All right. So this is the end of the section.